Okay, yeah. Today we have a speaker, Dr. Miklos Farfia from Budapest University of Technology and Economics. Yeah, he will talk about matrix means in several variables for about 45 minutes. Welcome.
Thank you.
You better use mouse.
Maybe this is also. Okay.
Yeah, there are some needs.
Okay. I would like to thank for the opportunity to give this talk here. As you can see, the title is Matrix Means in Several Variables. We will be covering some topics about how to extend matrix means to several variables. Therefore, as a first step, we have to consider what are two-variable matrix means. Actually, we'll denote with Pn the space of Hermitian positive definite n times n matrices. And we will be defining a two-variable function on this positive cone, which will be called a matrix mean if the following properties are met. The first property is idempotency, which means that if we take the mean of the two same matrices, we will get the same matrix again. The second property is, we can call that in-betweenness property, which is actually tells us that if xn is smaller than or equal to y with respect to the positive definite ordering, then the mean should be in between x and y. The third property is monotonicity in both variables.
I will show you how this system works.
Okay.
So all of your activities will be recorded. So students can read you. So you better use this mouse
All right.
and use this.
Okay.
Then I will give you a present after your talk.
Okay. I'm sorry. This was not clear from the first point. So as we can see, the third property is monotonicity in both variables with respect to the positive definite ordering. The fourth property is positive definite order. So this means that x is smaller than y if y minus x is positive definite. So so we have monotonicity with respect to the positive definite ordering. We have continuity in both variables, and there's a fifth property which is maybe non-trivial at first glance. That is the transformer equality. If these properties hold, then by Kubo-Ando theory of two-variable matrix means, we can find an operator monotone function f, which is normalized, which means that f at 1 equals to 1. And for every two-variable matrix mean, there is such an operator monotone function. So actually, there is a natural isomorphism between these two-variable matrix means and between the operator monotone functions which are normalized. So the question is how to extend such a two-variable mean to several variables. One way to go is the so-called iterative mean. This is based on a definition. We are going to need an infinite sequence of graphs which has the following property. Let G be a directed graph with n vertices and n edges, such that the undirected version of the graph contains a cycle which is Hamiltonian and Eulerian at the same time. This means that the graph will be isomorphic to this graph if we don't care about the directedness of the edges. And we also suppose that we have labeling for every vertex and every edge from 1 to n. Now, let us suppose we have an infinite sequence of such graphs. We will use these graphs to extend a two-variable mean function to several variables by an iterative construction. The definition goes as follows. So we have n positive definite matrices, and we have an infinite sequence of graphs. Now, as an iteration step, we are going to compute two means, and in such a way that for every edge I, we take the head vertex and the tail vertex, and we have the corresponding matrices, and we take their mean. So actually, this geometrically means that we take the first matrix, the sixth matrix, and in this case, this defines we take the mean of these two matrices corresponding to these edges, these vertices, and we have another matrix, which will be labeled by 3. So in this way, we can compute another n new matrices, and we can use the next element of this infinite sequence of graphs to calculate another n tuple. Now, if we do this recursively, then we get a sequence of n tuple of matrices. Now, the first theorem says that if okay. Okay. So, for instance, that can be okay. We have 3 vertices. Let us label them like this. Let us suppose that the mean of the 2 corresponding matrices will be the next first element. The mean of the second and the third, or maybe this one, the second element, and this will be the third element. This means that we have an x1, an x2, and an x3. Now we take the mean of the first 2. Let's say these are the first elements, and this will be x1, 1. Now in this way, we have x1, 0, and x3, 0. Then we have x2, 1. And in this way, also. So, and we may take the same labeling as again. In this case, the infinite sequences of graphs will consist of these graphs, for instance. That is one possible definition. So, but this theorem says that any possible infinite sequences of graphs are good, and these sequences will converge to a common limit point. So each of the sequences are convergent and have the same limit point. All of them have the same limit point, as long as the matrix mean is smaller than or equal to the square mean. Here we can see the square mean. Now what does this mean? This might be confusing at first glance, because from Kubo-Ando theory we also know that the largest symmetric matrix mean is the arithmetic mean. Although in this case, the proof of this theorem could be modified to be able to show that the convergence takes place even if we have larger 2 variable functions which are not matrix means, but they are smaller than the square mean. So actually, generally, this already proves, if this theorem is true, this already proves the convergence for every possible symmetric matrix mean. Because every possible symmetric matrix mean is smaller than or equal to the arithmetic mean, which is smaller than or equal to the square mean. And everything is, of course, with respect to positive definite ordering. Now, because of the limited time, we skip the proof of this theorem. I will tell mainly the basics. The proof is based on very standard argument in analysis. Like, first of all, we show that the sequences are bounded. And then we consider subsequences. And we show that these subsequences are converging, their distances from one another are converging to 0. And after that, we will show that every subsequence has the same limit point. Therefore, the main sequences should be convergent. So the proof is based on this idea. Okay, it's much better this way. So, but we skip the proof. But what about the properties of this iterative mean? Well, the following 5 properties are fulfilled, of course, with respect to an infinite sequence of graphs, because actually it turns out that this mean is not permutation invariant, which means that the limit point may depend on the infinite sequence of graphs. But anyway, if we fix one infinite sequence of graphs, then the following properties will hold with respect to that infinite sequence of graphs. The first of them is like natural extension of the idempotency property. This means that the mean of the same matrices is again the same matrix. The second property is an extension of the in-betweenness property, although we have to notice that this minimum and maximum may not exist. But otherwise, if it exists, then the mean should be in between. The third property is monotonicity in each of its variables. The fourth property is continuity, and the fifth, again, this transformer equality. Actually, I would like to note that the fourth property is an immediate consequence of property 3 and 5. So actually, if we have an n-variable function which fulfills this property and this property, so monotonicity and transformer equality, it is automatically continuous. So these are the properties. Now, yes, these are some properties given as propositions. Now, what about the numerical properties of this iterative mean? Now, first of them, it should be noted that the iterative mean is directly based on the 2-variable mean function. So therefore, we doesn't have to worry about recursivity. For instance, in the Ando-Li-Mathias mean, as we will see later, that is based on the n-1 variable mean to construct the n-variable one. Therefore, it is computationally problematic, because the n-variable mean is defined from the n-1 variable one by a similar iterative procedure, limiting procedure. Therefore, it is hard to compute even for 4 variables. This is a very good example, is the geometric mean, when we want to compute the 3-variable geometric mean, which is based on similar procedure. We are going to have problems if we want to go to 4 variables with such a definition. But this definition doesn't suffer from this kind of recursivity. The convergence rate of this iterative mean is linear. This actually I've been able to prove this only in the case of metric spaces, as we will cover them later. So actually, in the matrix case, when we take means of positive definite matrices, I've already only showed the global convergence takes place, but I didn't show it that actually it is linear. But it is quite so very likely it is linear. So yes, we will speak about the convergence rate later, because it is based on some property in metric spaces. As we can see, we can have several infinite sequence of graphs, and we may ask for which infinite sequence the convergence is the fastest. We can have some idea about this, but we will speak about it later. The iterative mean, as I've said, that is a disadvantage, that it seems to depend on the infinite sequence of graphs, so it is not permutation invariant. Although, in the trivial cases of the arithmetic and harmonic mean for positive definite matrices, we get back the corresponding n-mean. And in the case of the geometric mean for scalars, we get back again the n-variable geometric mean. Although, in the matrix case, we don't have a well-defined n-variable geometric mean, although there are several definitions which we have in the literature. So this could be one possible definition, if we fix an infinite sequence of graphs. Now, let us turn to the Ando-Li-Mathias mean. Now, this mean was defined for the geometric mean, mainly, and it is based on a similar iterative procedure. We consider, first, n positive definite matrices. And we take every n-1 combination of this n-tuple, which is done by this zi operator here. This is actually takes an n-tuple and leaves the ith term out. Now, we suppose that we have a sufficient definition of an n-1 variable mean. Then in this way, there are n possible such combinations. So we take their mean. We have again n operators. And this can be done recursively. So a theorem says that actually the convergence of this procedure for the geometric mean was proved by Ando-Li-Mathias back in 2004. It was an influential article about extension of matrix means to several variables. Actually, I've been able to prove the convergence for all possible matrix means, not just for the geometric mean. So actually, this is the next assertion says this. So if we start this procedure with a two-variable matrix mean, and this way we define a free variable one, and again we use that free variable one to define a four variable one, and so on, then all these sequences will be convergent and have the same limit point, which is defined as, for instance, in the case when we take n-1 means here, we define the n means such a way that these sequences are convergent and they have a common limit point, which is defined as the n mean. Now, actually, this convergence takes place if the mean is smaller than or equal to the square mean again, which means automatically it is true for all possible symmetric means. Well, what are the properties? We are going to skip the proof again because of the time limit. So, but what about the properties? We have the same properties as in the case of the iterative mean. So we have that n mean of the same matrices is again the same matrix. We have again in-betweenness property and monotonicity, continuity, and transformer equality. And again, continuity is proved as a consequence of property 3 and 5 together. All the other properties are proved inductively. So actually, it is the proof of this assertion is a generalization of the proof of the iterative mean, because the iterative mean could be treated as where n is just a variable. But here we have to go, we need an inductive approach. So we take the n-1 and then prove from that the n variable case. And this holds for all the properties except continuity. So we skip the proof. It is based on a very similar argument. We are going to talk about the elements of this proof later in metric spaces. Now, numerical properties again. Well, the first property here is that the Ando-Li-Mathias mean, as we have said before, is recursive. Therefore, it is problematic for n bigger than equal to 4. So it is not so easy computationally, although it has a linear convergence rate, which is explicitly proved only in the geometric mean case. And in the other cases, it is also very likely to have at least linear convergence. Well, in this case, the Ando-Li-Mathias mean is permutation invariant, which is a very good property. And we also have that in the trivial cases, we get back the corresponding n means. So it is also a good definition. What about weighted 2 means? What we know is that, for instance, in the arithmetic mean case, there is a natural extension of the arithmetic mean to a weighted arithmetic mean. We can see it in 2.14. Now, it is a geodesic line in Riemannian space, which has a corresponding distance function. This is actually a Euclidean space. So it has some very nice properties. In such a way, we can define a weighted harmonic mean. We also have a corresponding Euclidean space. This is not trivial, but actually this space is can be realized as a pullback metric. So there is an isometry, which here in this case inversion is the isometry. So there's an isometry between this space and this space. So therefore it should also be Euclidean. And in this way we can define the weighted harmonic mean as a geodesic line connecting x and y. Now there is also a weighted geometric mean. This is also defined as a geodesic, but the corresponding space is not Euclidean, but it is also a quite well-known metric. This is called a so-called trace metric. This has a non-positive curvature, which means that actually this is a symmetric space. So it has several nice properties. And its Deran factors, the first of them is Euclidean, and the second one is negatively curved. Therefore, it has non-positive curvature. So, but in a general case, we don't have corresponding Riemannian or any sort of metric space to a matrix mean, because if that would be the case, then we can easily define our weighted mean as a geodesic line connecting 2 points, and the mean itself is just the geodesic midpoint of the geodesic. But actually, we don't have this, although I think this is a very nice research problem, and one can be interested to find other Riemannian or for instance, Finslerian metrics, which the corresponding midpoint, where the corresponding midpoint map is a matrix mean. Now, but anyway, we can define weighted mean in the case when we don't have a corresponding metric space. It is defined as the following. Okay. Suppose we have a 2 mean, which is symmetric. In that case, we want to define a weighted counterpart for t in the 0-1 interval. What we do, we can do an interpolation to get this point back, with starting from these 2 points. We take so we take the midpoint of it. You can see that this midpoint is okay. So we take the midpoint, and we take the midpoint again, and we see that t is in between these 2 midpoints. Then we take the midpoint of these 2 and these 2, and this way we can interpolate this point, so we can get back as a limit. Actually, this seems to converge to for any possible A and B and symmetric matrix mean. So if the convergence takes place, then this defines a weighted 2 mean, which has the following properties. The first of them, again, is idempotency. The second one is in-betweenness. The third one is monotonicity. The fourth one is the compatibility with the 2 mean, which generalizes this, which we want to generalize with this procedure. The fifth one is that in the case of the arithmetic, geometric, and harmonic mean, we get back the corresponding weighted means. This is a consequence of the corresponding metrics we have, Riemannian metrics. Now, the sixth property is a very important one, that if we have a 2 mean, which is symmetric, two means, and they have this kind of ordering, then it automatically follows that the weighted means for the same t have also the same ordering. Now, MTAB is also continuous in A and B, and this is again a consequence of property 6 and property 8. So, and property 8 is again transformer equality. Now, for this weighted means, we can define the Bini-Meini-Poloni mean. Actually, this mean is also defined as an iterative, with an iterative procedure. Here again, we take
this operator, which leaves the ith term of the n tuple. We take the n minus 1 mean of it, and we take the mean of the left out matrix and the mean of this n minus 1 tuple at n minus 1 over n weight. Now, actually, in the case of Euclidean space, this is nothing but the Riemann centroid. Therefore, for all possible i's, this is just the same point if the space is Euclidean. But in general case, we don't have this, although we have the following theorem, that if we inductively define this mn by extending first from the 2-variable one and going to 3 variables, and then using the 3-variable one and the 2-variable weighted one to have the 4-variable one, and so on, then these sequences will converge if the first mean is smaller than equal to the square mean. This is actually, again, implies this theorem for all possible symmetric means. Now, we again skip the proof, although it is also based on an inductive argument. Let us turn to the properties. Well, not so surprisingly, we have, again, the same properties. Therefore, we have the idempotency, the in-betweenness, the monotonicity in its variables, the transformer equality, and continuity, again, as a consequence of the transformer equality and the monotonicity. Now, let us turn to the numerical properties of the BMP mean. The Bini-Meiney-Polony mean, again, is recursively defined. Therefore, it has the same problem as the Ando-Li-Mathias mean. Although the convergence rate of the Bini-Meiney-Polony mean seems to be cubic. Actually, this was proved by the article of Bini-Meiney-Polony, where they first defined this mean for the geometric mean case. And actually, in that case, they proved that the convergence is cubic if we are in a small enough metric ball. But generally, they also proved that the algorithm is globally convergent, although they can only prove the cubic convergence in a small enough metric ball. But anyway, this mean is also permutation invariant, like the Ando-Li-Mathias mean. And in the trivial cases, we again get back the corresponding mean functions. Although I have to note that the arithmetic mean and the harmonic mean case, the corresponding metric space is Euclidean. Therefore, at the first iterational step, we already have convergence, because at the first iterational step, we get back the Riemann centroid. So that's it, and we don't have to care about the other iterational steps. So it's not quite interesting in that case. Although in the case of the geometric mean for scalars, this is again goes to the geometric mean at first iteration step. Now, let us turn to metric geometry and CK domains. We will be defining our procedures, the iterative mean, the ALM mean, and the BMP mean in a metric geometric setting. Now, let XD denote a complete metric space. The first definition, we will give a definition of geodesic lines, or to be more specific, minimizing geodesics. Let gamma be a mapping between some real interval into the metric space X. And we say that this gamma is a distance minimizing geodesic between its ending points if the following is fulfilled. We are going to define geodesic length spaces based on this definition. XD is called a geodesic length space if there is a minimizing geodesic for every x and y in the space, which connects x and y, and it has a length the same as the distance of x and y. Now, in this case, we say that XD is a geodesic length space. Now, CK domains. CK domains are a subset of these kind of metric spaces. Let us suppose that we have a k between 0 and 2. And we say that an open set U in a geodesic metric space, XD, is called a CK domain for this k, or for some k. If for any 3 points, x, y, and z, we connect x and y with a minimizing geodesic gamma, For that, gamma, we have the following inequality. Now this says that actually we have a geodesic, that is x and y. We have some point z here. And this means that the distance, square distance of these 2 points is less than or equal to the square distance of x and z multiplied by 1 minus t plus the square distance of z and y multiplied by t and minus some factor. Now what is this factor? Actually, if k equals to 2, then this is just a non-positive curvature in the sense of Alexandrov for a metric space. This means that if we have our metric space is a Riemannian space, then it is automatically non-positively curved everywhere if the space fulfills its inequality globally for any x and y and z. But actually, if we let this k to be smaller than 2 but larger than 0, this means that we let the space have a bit of positive curvature. Actually, it was proved in 2007 in an article of Ochta that these spaces, the spaces, CAT1 spaces, which have curvature bound 1 from upper curvature bound 1, then if the space has small enough diameter, it is automatically a CK domain. Actually, for instance, in the case of the sphere, this means that the northern hemisphere, although it is uniquely geodesic, it is not a CK domain. But if you take a subset which has diameter less than p over 2, then it becomes a CK domain. So actually, this inequality lets us to have some sort of positive curvature. Now, we will call a geodesic metric space XD. We say that it is K-convex if this K is, if it is a CK domain. And we say that it is locally K-convex if we have, every point has a small enough neighborhood which is a CK domain itself. Now, what are the properties of these spaces? First of them, if we have an open ball, BXR in a CK domain, then for any 2 points in that open ball, there is a minimizing geodesic between them. In particular, this means that any 2 points can be connected by a unique minimizing geodesic. The second lemma says that if we have an open bounded subset S of a CK domain, then there exists a unique closed ball with minimal radius containing this S. And the third lemma says that every BXR, which is a subset of D, where D is a CK domain, that BXR is a geodesically convex set, which means that that every geodesic which connects 2 points in BXR are an element of BXR. Now, by these 3 lemmas, we can define the geodesic convex hull of any subset S. That is actually the intersection of all convex sets containing S. Now, how we can construct this geodesic convex hull? There is a natural procedure. We start with taking points from S and connecting all possible points with the geodesics. And we define the next set by the union of points of these geodesics. Now, we do this recursively, and it can be proved that in a CK domain, this procedure converges to a unique set, which is the geodesic convex hull of S. Now, we are going to study our iterative procedures in CK domains. The first theorem says that if we have a XD metric space, which is a complete K-convex geodesic metric space, and we have n points in that metric space, and we use the same iteration as in the case of the iterative mean, although as the matrix mean MAB, instead of a matrix mean, we use the geodesic midpoints connecting A and B, then this procedure converges to a common limit point. Now, we go into the proof of this, and this will make some clearance to the proof also in the matrix mean case. First of them, we take these inequalities, the k-convexity inequalities. For instance, we have a graph, and we need to take the midpoints here. And for every midpoint, we can write up the k-convexity inequality, this here, 3.1. And we have n such inequalities for every edge. And if we sum them up, then we get 3.2. Now actually, on the left-hand side, we take the distances from an arbitrary point, x, small x, in the metric space. This is AL. So AL is just the sum of squared distances from the points, the x QIL squared. Now, this inequality says that AL plus 1x is smaller than or equal to ALX minus a factor, which is called EL. That is actually the sum of squared distances measured over the edges of the graph. Now, multiplied with this factor k over 8. Now, so we have this corresponding inequality, 3.3. And actually, using this inequality, we can prove the convergence to a common limit point by the first step is that ALX is always positive because it is the sum of squared distances. We have that this ALX is a decreasing sequence, and it is bounded from above by 0. Therefore, it is convergent. But this again says that these ELs should converge to 0, which means that our points, because EL is nothing just the sum of squared distances measured over the edges here, taken over the edges here. So actually this says that the points are approaching one another. But this is not enough for the convergence, of course. The convergence follows from by bounding the diameter of this set. And actually it can be bounded by EL. And therefore every point is convergent. And these are all, so we can take the geodesic convex halves and they form a decreasing sequence. Therefore, it follows that these sequences are Gaussian. By completeness, we have the convergence. But we can say more in the metric space case, because actually similar inequality can be proved for the matrix mean case, although only for one, because we don't have corresponding Riemannian metrics to matrix means. So we have to choose one metric. One good choice is the Euclidean metric, which is induced by the Hilbert-Schmidt norm. And for that, we can prove an inequality, but not for any x, just for the zero matrix. So in that case, this inequality is only true for the zero matrix. Therefore, we cannot estimate the rate of convergence. But in the metric space case, we can do. So this is the next theorem, which says that the rate of convergence to the common limit point denoted by R is linear by this factor. Now, this is stronger than in the matrix mean case, because in the matrix mean case, we cannot even say that the convergence should be at least linear. Now, the proof of this, I think I omit the details, but actually it is based on some inequalities and the triangle inequality. And actually what we do is use this 3.3 inequality. We divide by ALX, and we bound this term, EL over ALX, and that's it. And actually, if we do that, we get this bound. Now let us move on to the center of mass in CK domains. How do we define the center of mass? Actually, this is the solution of the following minimization problem. This is that we have n points in the space, And we take the sum of squared distances from these points and from an arbitrary point. And we seek the minimum of this function. And the minimum fulfilling is just the center of mass, y. We denote it by y. Now, actually, it can be proved that a unique solution exists to this minimization problem if the space is a CK domain. It follows from the uniqueness of geodesics, strict geodesic convexity, and the continuity of the cost function here. This is a continuous function. So we have another theorem which says that we have our iterative procedure for this n-tuple of points from the metric space, and we can also define their center of mass. And actually, these points are generally not the same, as numerical experiment shows, but their distance can be bounded, and this is a bound for their distance. This follows from the inequality, again, for the AL axis. Now, actually, this inequality here, this is true for all possible, not just for the Riemann centroid Y, but actually it is true for all possible points in the metric space. So here we can put also X. This is also true, remains true. Now, another proposition. So we know that as numerical experiments tells us that these 2 points are generally distinct, but in the case of Euclidean space, these 2 points are just the same. How to prove this? This is very easy because we have this inequality. Now, if we have a Euclidean space, then actually this inequality is based on the CK domain inequality, but that is a natural generalization of non-positive curvature, which is defined as by the semi-parallelogram law. But in the case if k equals to 2, and in the case of Euclidean space, here this inequality becomes an equality, actually, and k equals to 2. So that is just parallelogram law for the Euclidean space. What we do is minimize both the left and the right-hand side, and we conclude that the ELs are independent of X. Therefore, the left-hand side and the right-hand side attains its minimum, its unique minimum at the same point. Therefore, this means that our iterative procedure leaves this point, the centroid, invariant. Therefore, it should converge to the centroid. That is for Euclidean spaces. Now, what about the other two iterative processes, the Ando-Li-Mathias mean and the Bini-Meiney-Poloni mean? Actually, these are also turned to converge as long as we define our weighted mean as the geodesic line connecting A and B. In this case, we also have convergence. The Ando-Li-Mathias mean converges also linearly, surprisingly with the same quotient. And in the case of the BMP iteration, so the Bini-Meiney-Poloni mean, we have also linear convergence, although I've used quite rough upper bounds and this kind of inequalities. So there might be much better convergence rate results which could be carried out. So this was done by a very rough estimation from above. So actually, in the case of the geometric mean, it is already known that in small enough metric balls we have cubic convergence. Now, what about the geometric mean? As we have already showed, the geometric mean of two positive definite matrices are defined in such a way. Actually, this is just the same for scalars as the ordinary geometric mean. And a very important property is that we have a corresponding Riemannian space where this map is a unique geodesic midpoint. Actually, this Riemannian manifold has a distance function as 4.3. And actually, this is an interesting Riemannian space because it's not Euclidean. Because if it's Euclidean, then everything is just going to Riemann centroid. That's not too interesting. But if we have, for instance, non-positive curvature, as in this case, then it's much more interesting to talk about this space. Actually, this Riemannian space is also Riemannian symmetric. So it has a isometric group G, which equals to the general linear group, and it has an isotropic group at the identity, which equals the unitary group over the complex field, and its action on the quotient space, which is in this case the space of the convex cone of positive definite R times R matrices. It acts like this. So these are the isometric transformations of this space. Now, the ALM and BMP and iterative mean converges for this mean. We have better results because the BMP mean is cubically convergent, and it is also shown by Ando-Li-Mathias that ALM, their procedure converges with a quotient rate of 1/2. So we have better convergence rate results. And we have also Riemannian mean defined on this space as the center of mass of the starting points. Now, this unique point, can be characterized by the following equation, 4.4. This is just, we take the gradient of this cost function, and this gradient should be 0. And this equation is based on that fact. Now, the gradient could be defined in this explicit form. And actually, this point, this is a nonlinear matrix equation. Therefore, it's not easy to find the unique solution X. Actually, it cannot be written in explicit closed form so far. But this point can be found by an iterative process, for instance, gradient method or Newton method. And we can estimate the distance of the solution of this point and from the other iterative procedures. For instance, here we have the convergence of two different iterative mean procedures, which is defined first by using this procedure with this infinite sequence of graphs. So all the time we use the same graph. And in the other case, we speeded up the rate of convergence by, if we take again this inequality, we can speed up the rate of convergence if we maximize EL. And that is actually, we have endpoints, and we are looking for, this is actually the traveling salesman problem, although we are not looking for the shortest distance, but the longest distance. And in this way, we can speed up the rate of convergence, and this is how iteration 3 has been carried out. And the gradient method actually is converging to a different point. As we can see that here we measured the distances from the estimated limit point of the iterative mean procedure. And as we can see that the gradient method converges till up here, and then it starts there. So the 2 points have, they are not the same, actually. So we can carry out also use a Newton method. And in this case, it turns out that although the Newton method converges much faster with respect to the number of iterations we should do, actually it is very costly to carry out the Hessian of the squared distance function, because we are on a Riemannian space which is not Euclidean, therefore it has varying curvature, and by this fact the calculation of the Hessian of the squared distance function is very complex. It requires a lot of calculations, and although the convergence rate with respect to number of iterations is much less than any other procedure, although it takes much more time because of the calculation of the Hessian is very complicated. And one thing I like to say about that, here actually we can see how the number of matrices. So we have the elapsed time of one iterational step in logarithmic scale on this axis. And on the other axis, we have the number of matrices for which we do this iteration. And it turns out that although iterative mean for this maximized EL is converging much faster than the other iterative means, but it is hard to solve the traveling salesman problem for it. So as n decreases, we know that it is a NP-complete problem. So it has a sufficient, significant impact on the elapsed time for one iteration step. Okay, thank you very much. Any questions?
Any questions? Sakshi? Tinka? Any? Yes. I'm good. Yeah.
Why matrix mean is important? We've already defined two variable matrix means by the Kubo-Ando theory. So we might be interested how to define a several variable form of matrix means. And there are several different procedures. For instance, the first procedure, which was considered by Ando-Li-Mathias, there is one possible procedure. We have also the Bini-Meini-Poloni mean procedure. And these procedures are only defined for or proved to be converged to the geometric mean, for the geometric mean case. But till now, it was not proved that that these procedures converge for any possible matrix mean. And actually, this was carried out here. So actually, these procedures, both of them, and the iterative mean procedure as well, converge. And actually, the iterative mean procedure is, although it is not permutation invariant, it is easier to compute because it is not recursive on F. So, and we can get a lot of inequalities by defining n-variable matrix means. So, I think the matrix mean case is also very interesting, not just the matrix space case, where we take the mean as a geodesic midpoint. Square mean. If the in a positive definite order, with respect to the positive definite order,
like arithmetic mean,
arithmetic mean.
vectors, is there a connection with the square root 8 times like geometric mean for vectors?
You mean how the matrix geometric mean is defined?
I mean, here is matrix mean,
Yeah.
and this is just square root 8 times b.
But
Is there a connection?
The problem is with that equation that is not Hermitian. A times b is not generally Hermitian, although a and b is Hermitian, but their product is generally not. So it is problematic to take square root.
Does not belong to
The same set, yeah. I mean the set of positive definite matrices. So the problem is the
This question is like any symmetric mean and geometric mean has some order relation. You want to ask some order relation about the symmetric mean and geometric mean. But
Actually,
you know about any symmetric mean is less than
arithmetic.
arithmetic. So yes, how about
Yes. So generally we have that we have a one-to-one correspondence between operator monotone functions and matrix means. And these operator monotone functions should fulfill another property if we want the corresponding mean to be symmetric. That property is actually ft equals to t times f1 over t. If this is fulfilled, then the corresponding MAB is symmetric. Now, for these kind of operator monotone functions, we also have, should be normalized, otherwise the first property, the idempotency property, is not fulfilled. So we should have these two properties next to the operator monotonicity of F. Now, this operator monotone function to the geometric mean. The smallest such function is the 1 plus x. This is the corresponding operator monotone function which corresponds to the harmonic mean. Actually, these were proved in 1980 by Kubo and Ando, and they defined these matrix means, and they proved that every such matrix mean which fulfills the 5 properties and the symmetricity property, is symmetric in its variables, is defined by operator monotone function in the following form here. So, in this way, it was characterized that the largest symmetric mean is the arithmetic mean and the smallest is the harmonic. Actually, in between we have a lot of possibilities. And actually, these the operator monotone functions are also characterized by, they have an integral characterization by some positive finite measure. I can, okay, I think I can write up how they look like. Every such function has a characterization of where this is a positive finite measure. So these functions are characterized in this form. So actually, these functions are very well characterized. So therefore, the matrix means are as well characterized.
Okay. One last question, if you have. Okay. I might missed from what you talked, but just what's the clear application? The geometric means and algebraic means has lots of applications. What's the clear the use of this matrix means?
Yes. Well, at this point, the geometric mean has a corresponding Riemannian metric. Therefore, it can be used to several problems. In the other case, we don't have corresponding metric spaces, which would be great further property, but this is not resolved so far. So this is an open problem. Generally, it is. So we can use them in inequalities, I think.
I see. Who is the workers that works on this area in Japan after Ando and Kubo?
We have also Professor Yamazaki.
Yamazaki.
I think we have other professors, or I can. I'm sorry, but I cannot remember
I see.
the exact names.
I see. Yeah. I have seen those names before, but I haven't seen the consequences recently. But you are working on it. I'm glad to see. Yeah. Any other questions? And thank you for the speaker again. Thank you very much. Okay, so I will.